This is 1984 Colorado Met Olympiad, problem number 5, and here is a view of this problem. We're told about 41 rooks that are placed on a 10 by 10 chessboard. Let's go ahead and draw that chessboard. Okay, so we have our 10 by 10 chessboard. Now, we would like to show that when we place all these 41 rooks, we can always find 5 of them that do not attack each other, regardless of the initial distribution of these 41 rooks. Alright, so I will be providing at least 3 different solutions. All the solutions are given on Soifer. Soifer's Colorado Met Olympiad book. It's a pretty good, decent book. It's kind of a medium to medium hard level problems. Nice combo problems as well in that pretty nice book. So how should I proceed, right? So what matters here? So, do I have to worry about where to place those 41 rooks? Not at all, right? So instead, I will be considering a pigeonhole type of argument. Recall that we have 10 rows and 10 columns, and because we have 41 rooks, and indeed 41 is strictly greater than 4 times 10, that implies that there must exist at least one row. There exists at least one row with 5 rooks. Does that make sense? Because if the max is 4, if each row has at most 4 rooks, I would have a total of 40. But I know that I have a total of 41, so there must exist a row with 5 rooks. Without loss of generality, let's say that that's the row with 5 rooks. So let's go ahead and let's pretend they are those rooks are here, 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 and say here. Okay, so let's move on. Now, when you consider the remaining 9 rows, these 9 rows remaining, how many rooks can we have at most in those 9 rows? Now, it's a tricky question. The answer is not 41 minus 5. All we said was in row 1 we have at least 5 rooks, meaning row 1 can have up to 10 rooks. What we know for sure is that one of the rows, and we decided to call it row 1, has at least 5 rooks. So therefore we can have at most, remaining 9 rows, so everything except row 1, have at least 41 minus 10, which is 31 rooks. Does that make sense? But then, using a similar type of argument, we just realized that 31 is greater than 3 times 9. So if you say that each of these remaining 9 rows have 3 rooks each, in total we would have only 27 rooks. But we know in reality we have at least 31 rooks. So that suggests that one of the rows must have at least 4 rooks. Does that make sense? By Pigeonhole Principle again. So let's assume that those 4, that row is, let's call it R2, and I don't know, maybe it's here, one of them is here, here, and here. So therefore, Pigeonhole Principle guarantees us that there must exist one row from among those remaining 9 rows with at least 4 rooks in it. Alright, and we can continue this procedure in a similar way. Now we have a remaining 8 rows. excluding row 1 and row 2, which have at least 5 and 4 rooks respectively. So remaining 8 rows have at least, well, you can bundle up to 10 on each of the rows 1 and 2. So therefore at least 41 minus 20, which is 21 rooks. But indeed, 21 is definitely greater than 2 times 8, which is 16. So that suggests that for the remaining 8 rows, excluding row 1 and row 2, we must have at least one row with 3 rooks, because otherwise you realize that if all of these remaining 8 rows have 2 rooks at most, we won't have enough. We know that we should have at least still 21 rooks remaining. So there must exist another row, so call it R3 without loss of generality, and that row has at least 3 rooks, say here. And finally, so we have remaining 7 rows. Everything except row 1, 2, and 3 have at least, by now we understand the rule, 41 minus 3 rows, each one has 10 at most, so at least 11 rooks, and obviously 11 is strictly greater than 1 times 7, suggesting so each of the remaining 7 rows had 1 rook. That wouldn't be enough, so one of the rows, say R4, has 2. Let's say, I don't know, let's say here and here. And finally, we have 11 minus, okay, so 41 minus 4 times 10, at least there must still be 1 rook remaining, and without loss of generality, let's put that rook over here, and let's call this row 5, and let it be here. Does that make sense, what we did so far? So make sure you understand that we did repeatedly apply Pigeonhole Principle with 41 rooks first, and then so on, gradually reducing the number of rooks that we might have. Now I will use backward induction type of argument to eventually show a construction. I will show that there must always exist 5 rooks not in the same rows and columns, okay? Not 2 of them sharing the same row, or not 2 of them sharing the same column. So we always pick the rook on row 5. Now for row 4, we pick one of them, especially the one that is not on the same column with the rook in row 5. Does that make sense? For instance, in this case, it doesn't matter for us which of the 2 we pick, because they are not on the same column. So without loss of generality, let's say I can say pick this one. And so therefore I'm eliminating this column altogether. Now we are in row 3. Row 3 has at least 3 rooks, and I need to pick one of them. Luckily, even though 2 of the columns are eliminated, there will always still remain at least 1 column which I can choose. In this example, for instance, we had only one of them eliminated, so this one is already eliminated. I can't choose this one, but I am free to choose any one of the 2. But even if this star here was here, I could still choose an extra one, right? Because I have 3 rooks in row 3, and I have only eliminated 2 columns, so regardless I should have 1 extra remaining. So let's pick this one. So therefore now I need to eliminate this column as well. Now we are in row 2. We have at least 4 stars, but we eliminated at most 3 columns, so there will be 1 free variable. So let's pick this one. And finally I go to row 1, which I only eliminated so far 4 columns, so there must exist at least 1 rook in that column, say this one. We have actually 2 remaining, but regardless, even if they were all aligned, I would have still 1 more rook remaining there. And look at these 5 rooks. I started with just a random distribution of rooks, and then I was able to find 5 non-attacking rooks. And that's a beautiful solution. So this is our first solution. So Soifer in his book mentions two more solutions. Both of them are really beautiful. So let me go ahead and provide you with solution 2, which is really awesome. Just as a quick note, usually chessboard type of questions appear under combinatorics, and there's a lot of strategies involved that you can use, so it's really a very deep area. Sometimes you can use a sequential type of argument like we did here. This is a definite, we did a forward and then a backward sequential argument here. Sometimes you can have coloring type of arguments and many others. Okay, so now step 2, I start with a 10 by 10 board. And what I will do is I will roll it. So what, in a sense, I will glue this edge with this edge. So the resulting picture will look like this. So I did glue those two edges, say here, right? So, and now I have my 10 by 10. So these two edges are glued over here. And now I have my 10 by 10 board, but only such that they're all glued to each other, right? And obviously I don't have enough, I can't see the back side, but in the back side we will have the columns as well. Well, at least I should be able to see all 10 of the rows, so therefore I will try to carefully draw these at least, even though I wasn't able to show you all of the columns. I think it should be like this. 1 2 3 4 5 6 7 8 9 10. Yeah, that's it. Let me just remind you that I decided to join these two and glue them over here. And now I will apply the pigeonhole principle again, but this time instead of applying pigeonhole principle to the rows, I will apply it to diagonals. So here is one way to do it, right? So let me color the diagonals. Consider this diagonal. I start from this top and I circle around. As I circle around, I will be visiting all these. Does that make sense? The rest are behind this picture, so I can't show it to you really. But I'll do the same thing for all the diagonals. For instance, consider this one, which will be just here. Does that make sense? And then I will have another one. Color it green, like this. So therefore, all the diagonals are basically colored, right? So let me color another one. Say purple, like this. But why would I do that? So each of these diagonals will be my my buckets. Well, I don't have any other color left. Well, unless I do. I didn't realize we have so many colors available. I love this thing. Okay, so here is another one. Let's choose a few more colors because it's pretty awesome to paint with these colors. I think I have not used this one, I guess. Yep, that's a different color. All right, so but you can really color. Actually, let's also make it black color too, right? So black is an awesome color, like this. So these are black, and then maybe I can gray. Do we have gray? Yes, so gray as well. But what matters is we have 10 of these. Oh, and then well, we have one more. The last one I will leave it as white, so that's the remaining. Okay, there you go. So I have colored, so the one that I didn't color, pretend it's white. Does that make sense so far? Okay, I assume it does, right? So there you go. Now I have 41 rooks and 10 buckets. Does that make sense? 10 boxes. And here my boxes are of diagonals, right? My diagonals are boxes. So do you guys agree that I will have to put at least 5 rooks by Pigeonhole Principle, by PHP, by PHP? I will put 5 rooks in one of the diagonals. Haha. And boom, that solves the problem. Why is that? Because now that you pick, let's say that you decide to stay on the orange diagonal, and I just randomly pick five. Well, in this case, because I can't see the rest, I can see the behind. I decided to pick these five. When I expand it, when I unfold this cylinder back into this thing, this shape, you know what will happen, right? None of the rooks will attack each other, right? Why is that? Because obviously all of the rooks are from different rows. These were the different rows, and the columns are also different, and boom, that solves it. So by just a single application of PHP, we are done. That's just an amazing solution. This is the power of making use of the geometry. And finally, the last solution. This one is more like an algorithmic solution by a computer scientist. But the main idea is the following. I can apply, in a sense, some... let me quickly draw the picture one more time. There you go. So now let's assume that it's not possible to find 5 rooks that are not attacking each other. So that we have at most, we have assume to the contrary, that we can find at most 4 non-attacking rooks. So we'll show that this will create a contradiction, right? And what I can do for these 4 rooks, I can put them, without loss of generality, I claim I can put them like this. And just to convince yourself, if you start with any random ordering, let's say you start with this ordering of these 4 rooks are like that. So let's do it like this. Suppose that those 4 rooks are here. They are not attacking each other. And suppose they are like this. All I do is start with the first one. For instance, let's say this one. All I do is I switch these 2 columns without loss of generality. When I switch it, it won't do anything because I know that this one is, because this rook is not attacking the other 3, it doesn't share the same column, so therefore I can just switch them, and so therefore this guy will go over here. But then I can switch these 2 rows, and finally, boom, it will further go to that corner. So therefore it is possible for me to do the same thing for the other rooks as well. And oh my god, so I should double consider when I mess up a picture like that. But I hope it's clear that I should be able to, without loss of generality, place all of my rooks in those top left cells. Okay, so now we are done with the first part. Now I will divide the picture into 3 regions. So let's do it like this, into 4 regions, I should rather say, like this and like this. First of all, I claim that there is no rooks in this region. Why is that? Because if there's any rook here, that's your 5th non-attacking rook, and we found the desired contradiction. So therefore, no rooks in this region. No rooks in this region. How about these neighbors in the first region? Can we have all rooks here? Yeah, so these cells can have rooks. It really doesn't matter. So they might or might not have rooks on those. So let's just leave them like that. Actually, let me color them. So the yellow cells, they might or might not have rooks, and that's perfectly fine. It doesn't violate anything. Oh, sorry, this one. Now, the important one is what happens in this region here. In this and this region. Can we have rooks everywhere, or what are the constraints? I claim that we cannot have 2 rooks which are symmetrical with respect to this main diagonal. So for instance, this one, row 2, column 7, and column 2, row 7. this is not, I claim this is no good. Why is that? Because what I can do is I can remove this rook and I can just add these two, and boom, that solves the problem, right? So let me repeat. So let me get a different color. So let's do this. Do you guys agree that if I have these five, oh, that's nice, purple and okay, so these five, oh, sorry, that's the fifth one, are non-attacking, right? So so how do I know? Because obviously there's nothing in this column now that I decided to eliminate this guy, right? And there's nothing here, nothing here, nothing here, and so on, and nothing here. So therefore, nothing here. So that's very interesting. So in a sense, I'm talking about a pairing trick. So what I'm claiming is there's no way you can put in symmetrical things on those two regions, which there's 4 times 6, 24 cells on this region, 24 cells on this region. So when you look at these two guys, you can only have one of them a rook. Does that make sense? For each of these pairs, in total there's 24 here, meaning 24 here, so each one is paired. For instance, this guy is paired to this one and so on, and for each pair you can have at most one rook. So therefore we might have at most 16 rooks here in region 1, plus no rooks here, 0 rooks there. And finally for this region and this region, I can have, because I have at most 24, 4 times 6, 24 pairs, I can have at most 24 rooks there in those regions, but for a total of 40 rooks. But that's a contradiction. Why is that? Because I know I have 41 rooks. Not 40 rooks, I need one more rook, and as soon as I introduce that rook, it collapses the whole thing idea, right? If I put the rook here, I have an independent thing. I have a new fifth rook. If I put in any one of these, and then boom, I can use the argument that I mentioned, that we have a symmetrical thing which I can eliminate whichever one is in the symmetry on this among these 4, and boom, I have 5 non-attacking rooks. So that solves this really beautiful question and combo problem. I hope you enjoyed it. I highly recommend this book by Soifer, especially for those of you who are at the beginning of the Math Olympiad quest and you want a little bit fun as well, right? So and you want to build up some self-confidence. So that's a pretty good kind of medium level introduction to Olympiad math. All right, so looking forward to see you guys in our next lecture.